For you. I have a challenge for you. I had to say it for the microphone.
I have a challenge for you.
All right. If you look at my assertion, who does not have this sheet that they were supposed to pick up on the way in? Nobody. Who does not have one? Who does not have one? Anybody else not have one? You got one? Okay, hang on to this. This will be your homework assignment in about 15 minutes. Here's my assertion. My assertion is that there are 10 divided by 6 seconds in a week. 10 divided by 6. Is that supposed to denote inflection, Jesse? Is that what that means? Is to yell 10 really loud? Is that what that means? It means I'm excited about the number 10! It actually does not mean that. I'm just being goofy.
Are there actually that many seconds in a week?
10 divided by 6? We need to know what this guy means. That's my whole point.
Is there actually that many seconds?
We're going to find out. That's my assertion. That is my assertion. What the heck did I do? Oh, right there. It's snake with a bitch.
Is everything below?
Nope, not a variable. Not a variable.
Is it what I mean by variables is it like it's wait unknown? It is that same unknown every time.
Nope, it is not a constant.
So it's not like pi, we could multiply everybody's looking at it.
Yeah, it's so.
Everything to
So some of you have learned to use that great skill that you learned in lower grades called reading, and you figured out the answer. Well, let's do this. So that term that I kept calling 10 is actually what we call 10 factorial. I promise I am done yelling now. 10 factorial simply means the product of all the consecutive digits starting at 1 and ending at whatever the number is. So when I have 10 with an exclamation point, it means 1 times 2 times 3 times 4 times 5 times 6 times 7 times 8 times 9 times 10. Okay? It's a lot easier writing 10 with an exclamation mark than it is this hot mess, right? Now, when I say 10 with an exclamation mark divided by 6, in order to evaluate that, it might help me to look at it like this. Once you get good at the notation, you won't need to. But when I divide by 6, what happens to the 6's? They cancel out, okay? Now, so my assertion is that I did the canceling out right here, right? And my assertion is that this number, whatever this product is, equals 1 year. Meaning the same, that's how many seconds there are in 1 year. So, in order to figure out if that's the case, I also did something that you guys probably do in chemistry, maybe in physics, where we always used to call this unit analysis or dimensional analysis. Has anybody done that in either physics or chem? Nobody has. Okay. You ever wondered when you're doing computations, like there's 365 days in a year, right? Oh, I didn't want that. I'm sorry, not in a year, in a week. In a week. I said a year, I meant a week. Ugh. I got to change this. This is wrong. This is wrong. It's a week. This is a week. That was my assertion. And so that means I have to change this guy. So, here's what I do. As I start with 1 week, right? You write that down for nothing? Good. That would have been my April Fool's joke for you guys. Ah.
Right? I did it.
So, how many days are there in a week?
7.
7 days per week. Do we agree with how I wrote that fraction? Okay. And how many hours are there in a day? 24 hours in a day. I don't care how many hours there are in a week because I know how many. Well, look at this, Andrew. 7 times 24. That's how many.
So I was doing
Is that what you guys call it? Stoichiometry?
Where you gotta leave day,
Yeah.
hours, so they cancel out.
Bam! Bam!
Stoichiometry.
And then I got how many hours in, or I'm sorry, how many minutes in an hour?
How many seconds in a minute or tells you past?
Yep, and then seconds per minute is 60.
Now you confused.
Now I can cancel, right, Riley? I can cancel week. Let me do this in red. I can cancel week with week. I can cancel days with days. Hours with hours. Minutes to minutes. And what units am I left with? I'm left with seconds, right? So now all I have to do is do the math. Now, am I going to punch this into a calculator? I'm not going to. I'm going to do this differently. I'm going to break this guy. I'm going to break each of these guys down into their prime factors. And then I'm going to see if I can cancel them out with these guys. If I can cancel every prime factor with one of these guys, then I know that my assertion was correct. So, can I break 7 down into prime factors? No, 7 is prime, right? So that's just 7. How about 24? Can I break that down into prime factors? Can I divide 24 by 3? Yeah. And 3 is prime, right? Okay. And then what am I left with when I divide 24 by 3? 8, right? When 8 is 2 times 2 times 2, right? So 24 is 2 times 2 times 2 times 3. 60. How does 60 break down? 60 is 5 times 12, right?
So you're trying to find like the all prime numbers for.
I'm breaking each of these down. So this one right here is this guy. This one right here is these guys. This one right here is going to be 60 is 5 times 12, right? So I got 5 in there. And then 12 is 2 times 2 times 3. And then I got another 60 right here, right? So then I got 5 times 2 times 2 times 3 again. Okay? So these are my prime factorizations of all those conversions that I did. Now let's see if I can, do I have to pay attention to the 1? 1 doesn't do anything, right? I just ignore that. So I'm going to cross that out. Okay? How about this 7? Can I cross it out with the 7 up here?
Do it.
Yeah, let's do that. Get rid of that 7. Can I get rid of this 2 with that 2? Thwap and thwap, right? Uh-oh. I'm out of 2s. What's that, Mason? Oh! This guy's 2 times 2, right? That guy right there is 2 times 2. So I can take 2 of those 2's out with a 4. Whoa. Thanks, Mason. 3. Get rid of 3 with that 3, right? Look at the 5. The 5 This 5 can go away, right? What about that 8? 2 times, so this 2, and that 2 cancels out with the 8. Oh, that's 9, and then the 5 and the 2 cancel out with the 10. Look at that. 10 factorial divided by 6 is the number of seconds that there are in a week. Do we understand how this notation works? Do we understand the benefit of the notation? Now, you might be asking yourself, when would we be using this? Instead of just contrived problems by your teacher, when do you use this? You use this in probability calculations all the time. So if you go to your calculator, you don't see an exclamation mark anywhere here, right? Some of you might. Yeah, you got more buttons than Fort Knox, I'm telling you. But where do you see it on here? I think on this it's on stat. Nope. Nope, it's not on stat. What is it on? Is there a probability thing? Who's got a probability button on their calculator? Yes.
So if I were to multiply all of the numbers between 1 and 10 and then take that and divide by 6, would that be different from if I were to multiply them all together except for that 6 and then add by 6?
Same thing, right?
It would be the same.
Same answer. Same answer because multiplication is commutative, is it?
But you're dividing as well.
You are, but dividing is the same thing as multiplying by that, right?
Is subtraction the same thing as adding the reciprocal?
No, subtraction is the same thing as adding the opposite.
Oh yeah, that's right.
Yeah. Okay, now,
That's just, wow.
some of you guys, I don't know where to find it on this one. Where is it? Maybe in there? String, no. No, clear. I don't know where it is on this one. I'll have to find it. But, on a lot of calculators on this, does anybody have this calculator?
I have. I got it.
You'll see a PRB button on your calculator. That stands for probability. That should tell you where you see a lot of this type of calculation. Okay? We use a lot in computing probabilities. We use factorial a lot for that reason. So now that I've gone through that, I am going to skip the rest of this lesson. And we're going to go straight to the problem set. And for Wednesday, problem set number 1 and number 3 are going to be due. Okay?
Say that again.
Number 1 and number 3 of the problem set due on Wednesday.
All number 1.
All of number 1. The whole thing. So number 1 and then number 3. And that is due Wednesday.
Number 1.
Yes. Right there. Problem set 1 all and then number 3. Okay? Now, if you look at letter A should be fairly straightforward. It says complete the following table of factorial values. So if I look at the number 1 and I want to do 1 factorial, it's just 1, right? So that's 1. 2 factorial would be 1 times 2, which is 2. Very, very bland so far. Excuse me. There you go, Brooke, which is 6. Do we see how Brooke got that? 1 times 2 times 3. That's 3 factorial. And then 1 times 2 times 3 times 4. Now, do I need to go through 1 times 2 times 3 times 4? Or can I just say, well, 3 factorial is 6, times it by 4, and then I got 4 factorial. Does that make sense?
Oh, so we can just take.
You can just take this times 4.
Oh, that's fine.
That's a lot easier, and it's mathematically accurate, right? And then I take 24, that's 4 factorial, times it by 5, and I get 5 factorial, which is going to be 120. I'll let you guys do the rest of them. And then we get to do B, C, D, and E. Oh, and F. So, what did you get for 5, 6, or 6, 7, and 8?
6 is 7, 20. 7 is 50, 40. And then 8 is 43, 20.
40320. Okay.
It looks like negative 720.
It does look like, and that's what Trey wrote too. You are taking accurate notes, but let me fix my note taking.
Just use some common sense, really.
Yeah. But when you're behind the notes, it's kind of hard to use the critical thinking part, right? You're just too busy catching up.
What? Wait, what did you say?
So now,
That's what I was thinking.
how would you do letter B, Stephen?
1 over 1.
Yeah, 1 over 1.
But it's not 1, it's 1!
Yeah.
Which is just 1, right? So this equals 1 plus 1 over 1, which is the same thing as 1 plus 1, which equals deuce. Yeah, this is, letter C is, it says 1 over 1 plus 1 over 1 factorial, which we already know is that. And then 1 over 2 factorial, that's just 1 over 2. It's going to be 2.5. I can really just take this 2 and add a half to it, right? Now it says it wants us to do to 7 decimal places. It wants us to do 7 decimal places. So now we're out of Mr. Cook's favorite representation of rational numbers land in fractions. We're not doing fractions anymore. We're doing the dreaded decimals. And we're rounding to 7 decimal places. So here you should get 1 plus 1 plus 0.5. We're in decimal land right now, right? So 1 plus 1 plus 0.5 plus what's 1 over 3 factorial? 1 over 6. 1 over 6 is like 0.1866 and 0.1666. We're not going to do the repeating. We're going to do at least 7 decimal places so we can do this right. 6, 6, 7. And so I got 1 plus 1 plus 0.5 plus.
That's what 1/3 is.
No.
Oh, never mind.
No. 1/2 is 0.5. 1 over 3 factorial is the same as 1/6, which is this 0.1666667. Now I add all those guys up and I get what? You should get that. Rounded to 7 decimal places.
What does it mean, just like decimal places?
1 decimal place, 2 decimal place, 3 decimal place, 4 decimal place, 5 decimal place, 6 decimal place, 7 decimal places. So now, can I shorten this process? Do I have to write this whole thing out every time? Or can I just do 2.6666667 plus this?
You can do that.
Yeah, I can do that, right?
So desired.
I would prefer that if it's mathematically accurate. Jasmine, is it mathematically accurate?
We're always aiming for mathematical accuracy.
Absolutely. So it's, ooh, what, did you see that?
What
It moved by itself.
does it all the time?
So 2.666667 over or plus 1 over 24 now. What's 1 over 24? I don't even want to write that as a fraction. Who's got 1 over 24 already decimaled out? No, 1 over 24 first. I just want 1 over 24. 0.0416, and then we go into the 6 sevens.
There's 4 6.
6, 6, like so, right?
There was 1 4 6.
Well, this 0 is a decimal place here, so that's 1, 2, 3, 4, 5, 6, 7
How'd you get
decimal
that
places.
decimal?
What's that?
How'd you get that decimal?
This is 1 over 24 because 1 over 4 factorial is 1 over 24.
Is that 1 6 6 6 7? Is it all?
Yeah, that's a 6. That's not a 0. That's a sloppy 6. Now you're gonna make me get all OCD on us and do that. And then we do that addition, and what do I get, Mason?
2.70833.
Like that? All right. Now, it keeps going up, right? How far up is it going to get? So here's what you get to do. And I would do this on a separate sheet of paper because they want you to do it for k equals 5, k equals 6, k equals 7, all the way up through k equals 10. Meaning, you're going to go all the way up to 1 over 5 factorial, and then give me the number. Then you're going to do 1 over 6 factorial, give me the number. 1 over 7 factorial, give me the number. And keep going and doing that all the way up to 1 over 10 factorial. So I would strongly suggest, so that I can do well by giving you feedback, to do that on a separate sheet of paper. Now, before we do that though, does anybody have some thoughts as to what this number is going to do? Is it going to keep going up forever and ever and ever? Because it keeps going, it's getting bigger, isn't it, Mel? It's getting bigger. It's going up by a smaller amount each time though, isn't it?
Yeah.
Going up littler and littler each time. So, is it going to go up forever?
Yeah.
And if so, is it going to hit, is there a point which it will not go over? Will this ever get to 3? I guess is my question. Will it ever get to 3?
It's got to.
Let's do the thing up to 10. While you're doing that, I'm going to draw a picture. And maybe this will give you some intuition.
Good job.
Start at 0. So, let me ask you this. All you guys crunching your calculators. I should do this on the smart board. I'm going to do this on the smart board because I'm strange like that. I'm going to start at 0 and I'm going to go to 1. Now, let's say I am a frog and I can jump half a distance. I can jump half a distance. So if I start here at 0 and I want to end at 1, where can I jump? To what point? To 1/2, right? So I can jump to 1/2 then. Now, I'm at 1/2 now, and I want to get to 1. Where can I jump to? To 3/4, halfway between 1/2 and 1, right? So I went halfway. Now, at this table right here. Now I'm at 3/4. I want to get to 1, right? So I go halfway again. Where am I? Halfway between 3/4 and 1. 3/4 and 1 puts me where? 7/8.
Where you end up.
7/8. Now I'm at 7/8, and I want to get halfway, or well, I want to get to 1, but I can only go in halves, right?
Yeah.
So 15/16. Good. I'm going to stop putting numbers in now because it's going to get crowded. Now I'm at 15/16. I want to go to 1, but I can only go a half, right? So now I'm at, no, close. You got the denominator right. 31 30-seconds. 31 30-seconds, which is right about here. And now I'm going to go to my skinny marker because it's going to get even skinnier. 31 30-seconds, I want to get to 1. 64ths. 63 64ths, which is right there. And then Nick, the next step. Yeah, well, how many 124ths? 123. 123. 123. Am I ever going to get to 1? No. This is a name of a paradox. This is called Zeno's paradox. And a Greek philosopher named Zeno came up with this and said, I can never start at one wall and touch the other wall. Because in order to get to the wall, I have to get halfway there first. And then in order to get to the wall, I have to go halfway again. And then halfway again. And halfway again. And so, obviously, we know we can get from one wall to the other, right? But the paradox is, if I keep adding halves, I never get to 1. It is endless. So that should give you some intuition as to what happens with this guy. Do I necessarily get to 3? No. As a matter of fact, we get to a very specific number. When I do this calculation an infinite number of times, so not when k equals 10, but when k equals infinity, I get to a very specific number. And we call that number E. Who sees E on their calculator? E. E is Euler's number. Named after one of my math heroes, Leonhard Euler. If something was done in math, Euler did it. Not Euler. Not Euler. 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 He was Prussian, but did his important work in Russia, in St. Petersburg. Very important mathematician. Very important mathematician. And the value of E, little e, equals, somebody pump that out for me. Hit E on your calculator, please. $7.218. Oh, you guys are killing me. And then this is a radical. It's also a transcendental. It goes on forever. It does not repeat. It does not end. It's a radical. All right, ladies and gentlemen. I know I said I wasn't going to talk for a half an hour.